How do you do, ladies and gentlemen, and teachers, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And we come to another program on electricity, magnetism, and such allied subjects, which I have entitled Miscellaneous and Wondrous Things. Again, I emphasize the spirit that the language is intended to convey. Wondrous things, for indeed they are to contemplate. Consider the following. I have here two clear glass, incandescent, carbon filament, 110 volt lamps. That covers the description, I guess. I'm going to energize one of them. Now, I'm not going to tell you whether I'm going to energize it with alternating current or direct current, but I'm going to energize it. There it is. There is a flow of charge in the wire. The wire offers some resistance, gets hot, and emits light. Question, is that lamp energized with alternating current or with direct current? We shall investigate it. If the current in that filament is alternating, it first surges this away and then that away, 120 times per second on 60 cycles. It gives rise to a magnetic field, which is oscillating, changing. Accordingly, if I present an alien magnetic field to that wire loop, to that filament, there should be some interaction between magnetic fields. And we shall tell in a minute. Here is a horseshoe magnet. Watch the filament. Notice that very rapid oscillation. Clearly, that lamp is energized with alternating current. I leave it as an exercise for you to think about. Supposing I energize this other identical lamp, or indeed this first one, with direct current of the same voltage. The lamps would be identically bright, pretty nearly, which is a technical matter. And I ask, supposing I presented an external magnetic field to that DC energized filament, what would the filaments do? That's a very good exercise. Very good. Consider another very dramatic. Here I have a solenoid. A solenoid is a loop endlessly of wire fixed to a lucite plate. I am going to give rise to a current in that solenoid, in the wire. And a wonderful thing takes place. Here I will show you the solenoid. And let me energize it by impressing a difference of potential, as we say, 6 volts. A current is in this wire, and a wonderful thing is to be seen. That solenoid behaves as if it were a bar magnet. I'm going to show you that. I'm going to sprinkle some iron filings here at random. Sprinkle some iron filings at random. They have taken up a chaotic position. Chaotic. Now I am going to connect that coil to a battery and minimize friction a little bit by such action, and watch the beautiful pattern taken up by the filings. Watch it. There it is, beautiful, just like a magnetic field. And I call your attention to this very important thing. Very near the wire, the magnetic field is very strong, and so the filings are bundled up in little bundles. Let me just disturb that and put it in chaos again and show it to you once again. Watch the instantaneity with which the field takes hold of the iron filings and aligns them. Watch this now. Look at that. Incredible. Incredibly fast. Next demonstration. A very wonderful problem. Indeed, one which is not so easily answered. I have here 2 incandescent lamps. Here is one, and there is another, and I am going to connect them to 110 volts, 60 cycle alternating current. And they are in series. Here is the filament, and here is the filament. One of them, the small one, is an 11-volt lamp. Somebody says, oh, I've never heard of an 11-volt lamp. Well, when you deal with me and physics, you're likely to hear of very strange things. An 11-volt lamp. And this, 11 watts, 11 watts, excuse me, 11 watts, 11 watts, sorry. And this one is a 100-watt lamp, 100-watt lamp. Now they are in series. I connect them to the house line. Question, what will we see? What will we see? Will this one light up, as we say? Will that one light up? Or will they both light up? Now, you know my philosophy. I am not so ready with answers because I don't think answers are so important. What is important is that you think it out logically and rationally and come to a proper understanding. Because, as you have heard me say, it is not so good how much you know. It is most important how much you understand. So, I'm going to reveal to you what happens. Watch. I'm going to connect them. I'm going to connect them. Pretty soon, I'll connect them. Watch. Aha. The lower wattage lamp is energized and reveals some light. I want to know, why is it so? Indeed, this is a wonderful expression for you to carry with you all your life, asking, why is it so? That's a wonderful question. I have spent 60 years with that phrase, asking constantly, why is it so? Consider now the following. Here is a mechanism called a horn gap. Notice, shaped like a megaphone, like a horn, sometimes called Jacob's ladder. I have the ends of this connected to that high voltage induction coil. I'm going to give rise to a discharge at the nearest separation of the gap. Watch it now. Watch. I am energizing the induction coil with a 6-volt battery, giving me 150,000 volts across here or so. Watch. Whoop, I got a little, well, some strange things happen when you deal with electricity. Question. The discharge takes place across this narrow gap. I had hoped to find it climb up and show evidence of discharge at 3 or 4 inches, because I can get 3 or 4 inches here. I want to know why this discharge does not climb. I'm going to tell you why. It doesn't climb because ionization is not so readily accomplished in this region, and we need ions for electric energy transfer. Question, how could I get the discharge to climb the gap? Answer, by lighting a candle below or holding a match below, and the heat of the match or the candle would give rise to further ions which would aid the climb of the discharge. Now you say, well, why don't you do it, Professor? The answer is there is too much convection in this room, the hot air that I'm blowing, some would say, whereupon there is not the confinement of the heat energy that I want for convection. Now, one more enchanting question. I have here a cubical frame which I will represent on the board like this. There it is. And each edge of this cube has a resistance fixed to it. A resistance. A resistance. I won't draw the rest. Resistance, R, 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 R. Every side, correction, every edge of this cube has a resistance R. The problem is classic in this business. Supposing I consider this point A and a remote diagonal B. That is, these are the points, this one and this one. Question, what is the total ohmic resistance between this point and this point of this cubical structure of resistors? The total resistance between A and B. I'm going to give you the answer. The answer is that if R is the resistance at each place, then the total resistance between the extremities of the cubical diagonal turns out to be 5/6 of R. That is, if R is 1 ohm, then the total resistance is 5/6 ohm. I leave that as an exercise for you to do, because I remember meeting this when I was about 9 years old, and it took me 6 years to learn how to do it. See, 6 years. So what am I getting at? Do not be in a hurry to answer questions. Remember, the answer isn't important. It's how you think about them that's important. And I'll give you a further hint. There is not only one way to do it, there are 2 ways to do it. Indeed, there are 3 ways to do it. So you see how charitable I am. There are 3 possible solutions to the problem. Let's go further. Electromagnetic induction. Here I have a very strong alnico-magnet, and the gap between the poles is very tiny. You see a very tiny gap. Here I have an aluminum slab. Aluminum, remember, is not magnetic. Oh, correction, slightly magnetic. Now I'm going to drop this here in free space, as we say, and watch the rate at which it falls. Well, it falls like a freely falling body. Watch it. Incidentally, where did the sound come from? Answer, a vibrating system. So it fell under free fall. Now I'm going to let it fall in that gap. Watch it now. Watch it. I'm going to do it again. Notice how sluggishly it falls. Why? This is a conductor. It is moving in a magnetic field. The motion of a conductor in a magnetic field gives rise to a difference of potential. A difference of potential gives rise to a current. The current in the slab gives rise to a magnetic field, and magnetic fields interact with magnetic fields. Watch it. And that's Lenz's law again. Supposing I did this now, this was a solid slab. Supposing I did it with a slab that is slotted. I hope you see the slots, or slits, or whatever you wish to call them. I will show you that it will fall now much more fast, much more rapidly. There it is. And so we are coming to the close of another series of lessons, this last one on electricity and magnetism, a massively enchanting field for your exploration. And remember, whenever we think of anything, regard highly the national origin of the men whose industry and intellectual competence gave it to us forevermore. And I thank you for watching.